Given the function x cubed minus 9x, let's find the first derivative in critical numbers. Our first derivative, we have 3x minus 9, 3x squared minus 9. The critical numbers occur when this first derivative is equal to 0. So let's factor out a 3. If we divide both terms by 3, that leaves us with x squared minus 9. X squared minus 3 we can factor as x plus square root of 3 times x minus square root of 3. If you were to FOIL this back out, you would get x squared minus 3. This leading factor of 3 we can ignore because it doesn't have a variable. These other two factors do have variables, so when we set them equal to 0 and solve, we get negative square root of 3 and we get positive square root of 3. Critical numbers mark the x values of hilltops and valley floors. From the graph to the right, we can see that negative square root of 3 is the x value for a hilltop. Positive square root of 3 is a critical number, and it marks the x value of the valley floor. When you mark your critical numbers on a number line, you want to test around and between the critical numbers. And that's because we want to know the behavior of the graph anywhere around and between the criticals. On the left side of the critical number of negative square root of 3, in class we decided on negative 2. That's a good test number because it's easy to work with a negative 2 and it's smaller than that first critical number. Going to our first derivative, which was 3x squared minus 9, we sub in this test number and we get an answer of 3. Since that value is positive, that means our graph is increasing in this interval. We tested between the critical numbers, and 0 was a good choice because 0 is easy to work with, and it's a number between negative and positive square root of 3. The rate of change at x equals 0 was negative, and that meant our function was decreasing between the critical numbers. And then finally, we picked a test number that was larger than square root of 3, and we picked 2. That's a fine choice. It's easy to work with, and it's greater than square root of 3. Substituting into our first derivative, we got an answer of 3, which is positive, so we have a positive rate of change. When you look at the graph at the top right of your screen, the behavior and that number line match. We increase until we get to the first critical number, and that is true here. We decreased between the criticals, and that's absolutely true, decreased. And then we increased after the second critical number, increased. So it's all lining up, no pun intended. The intervals of increasing and decreasing, those use the first derivative. Those are rates of change, so they use the first derivative. Our function is increasing left of the first critical number and right of the second critical number. So the values of x from negative infinity to negative 3, or the values of x from positive square root of 3 to positive infinity, will give you increasing rates of change on your graph. The decreasing occurred between the criticals, and that was between negative square root of 3 and positive square root of 3. Relative minimum and relative maximum. Let's go back to the graph at the top of your screen. A relative maximum is any little hilltop. A relative minimum is any little valley floor. It doesn't mean it's the absolute greatest or smallest point, but it's just relative to a portion of the graph, it is the max and the min. Let's go back down. Negative square root of 3, let me point this out first. Our first critical number marks the hilltop. So we find that y value in the original function, that's going to be the relative maximum. The second critical number of square root of 3, that one we can tell marks a relative minimum. Now, because this is the original graph, we plug the criticals into the original function. So remember that when we go back down. When you're asked to find relative minimum and or relative maximum, use the original function. The minimum was when we used our second critical number, so the original function with square root of 3 plugged in is square root of 3 cubed minus 9 times the square root of 3. And this was approximately negative 10.4. The relative maximum occurred at the first critical number, negative square root of 3. Negative square root of 3 cubed minus 9 times negative square root of 3 was approximately positive 10.4. When you pair up the number you plug in and the answer you get, then you get the actual point on your graph. Let's go back up one more time. We can tell here that the first critical number gave us an answer of 10.4 when subbed into the original function. The second critical number of square root of 3 plugged into the original gave us a negative 10.4. So that's the relative max and that's the relative min. Let's do a second example and repeat. Given the function x to the fourth minus 4x squared plus 1, let's take our first derivative. That's 4x cubed minus 8x. These two terms we can factor out of 4x, and that will leave x squared minus 2. If we redistribute, that's 4x cubed minus 8x. This time our lead factor has an x. We'll fill this 2 in real quick. There we go. 4x is equal to 0 when x equals 0. Like the problem before, when we factor, we split up the difference of squares as x and x in the front, square root of 2 positive and negative in the back. This will give us the other two critical numbers. Now, if you look to the right at your graph, we expect 3 critical numbers because we have 2 valleys and a hill. That's 3 points of change. 0 marks the hilltop, negative square root of 2 and positive square root of 2 mark the valley floors. Let's go to the number line. We have 3 critical numbers to test around, and we're going to test them in that first derivative. So in red, you'll see your critical numbers marked. We're going to pick numbers between and outside of those critical numbers, testing them in the first derivative. So in our first interval, we're decreasing because we got a negative result from this test number. In the second interval, we got a positive result. The derivative gave us a positive or increasing rate of change. In the third interval, we had negative, so we're back to decreasing. And in the fourth interval, we got positive, so we're back to increasing. If you look at the graph at the top right of your screen, that matches up just right. Decreasing, increasing, decreasing, and increasing. Blues for decreasing, greens for increasing, and all that matches up. Now, further down, the intervals of increasing and decreasing, remember that those come from the first derivative. So we decreased left of the first critical number and between the second and third critical numbers. So decreasing was in the blue sections, negative infinity to negative square root of 2, and also between 0 and positive square root of 2. In the green zones, we had increasing, and that's between the first and second critical numbers, and also after the second critical number. Just make sure you see where those intervals match up. And I'm going to try to make a better looking 2 there, or at least make it look like a 2. As far as relative max and min, we have one relative max at the hilltop, 2 relative minimum, or minimas, that plural, at those 2 critical numbers. So when we go to the original function, which is back up here at the very top, We're going to sub in all these three critical numbers, and just keep in the back of your mind that 0 is going to give us a relative max. The negative and positive square root of 2's will give us the minimum. Here we go. Okay, so the relative minimum is where our original function takes the critical numbers negative and positive square root of 2. Those both yield an answer of -3. So your relative minimum value is a -3. The full point is the critical number you plugged in paired with the answer you get. So we have square root of 2 and -3, negative square root of 2 and -3. Those were those two valleys. The top of that little hill that was in the middle, because remember our graph was shaped like a smooth looking W, 0 is where that relative max will occur. Plugging that into the original function gives us 1. So the relative maximum occurs at 0, 1. So we have those values here and down here. Those are our relative max and min. When asked to find absolute extrema, like an absolute maximum or absolute minimum, we're going to find our critical numbers. We're going to take those critical numbers. We'll also be given an interval. We're going to plug the interval endpoints and any critical number inside the interval into the original function. And then we'll just look for our largest and smallest answers. So if you need to write these down or read these 3 steps, pause the video and just kind of take a look through these 3 steps. Those will get you to the point you need in your problem, though. All right, I'm going to go ahead and proceed. Give the absolute maximum and minimum of the function. So when you see that word absolute, you'll have a function and an interval. Take the first derivative, that's 3x squared minus 3. Factor out your 3. This breaks down to x plus 1, x minus 1. The lead 3 doesn't have a variable, so you can skip it. It won't yield a critical number. X plus 1 is equal to 0 when x is -1. X minus 1 is equal to 0 when x is +1. The interval we're given is -2 to +2. Both of these critical numbers fit inside this interval. In fact, over on the right where we have the graph, I highlighted in black ink the part of the graph in this interval from x equals -2 to x equals +2. So concentrating on this part of the graph, our critical numbers are -1 and +1. So there are actually 4 values to plug into the original function, x cubed minus 3x. So if you look down here at the very bottom of your screen, f of -2 is one of your endpoints, and it gives a value of -2. Let me fix the ink on that. F of +2 is the other endpoint, and it gives a value of +2. The critical numbers, both of them are inside this interval, so we put both of them into the original function, and we get f of +1 gives us -2, f of -1 gives us +2. And so as you go through, the lowest points on the graph have a y value of -2. The largest values of y on the graph in that restricted domain is +2. Let's do another example. Give the absolute maximum and minimum of the function. We have the function x squared minus 6x minus 2. but we're asked to keep the interval only between -1 and 5. So on this graph to your right, I have highlighted the portion of the graph that extends from x equals -1 to x equals 5. No less and no more. Only highlighted between -1 and 5. Our first derivative is 2x minus 6, which carries a critical number of 3. Is 3 inside this interval? It is. 3 is between -1 and 5. So we're going to find, using the original function, the values at the endpoints, -1 and 5, and also the value at that critical number that's inside the interval. Substituting in -1 gives us a value of 5, and so remember, -1, 5 has to be a point on the graph. We substitute 3, and our answer is -11, so 3, -11 is another point on the graph. And finally, we subbed in 5, and our answer was -7, so 5, -7 is a point on the graph as well. We have the beginning and ending point, and the point in the middle, because that was our critical number, it's at the valley floor. Now, it's judgment time. 5's our largest answer. That's the highest point in the interval. So that's our absolute maximum. 3, -11 was our lowest point on the graph in the highlighted interval. So that's our absolute minimum. 5, -7, it wasn't the highest or the lowest. It was just the end point of the interval. So for absolute, you look for your largest and smallest answers. I hope this video helps. I know there's a lot of math to keep up with on these types of problems, but keep practicing and keep working hard. Reach out by phone or email if you have questions, and I'll do my best to help you out.